Okay, this lesson is going to be on something called Euler's method. Okay, and I'm also going to review the tangent line approximation. Tangent line approximation. Okay, this is known as linearization. And Euler's method. Okay, Euler's method is used, okay, when you have a differential equation that is not separable, so you're not going to be able to solve it. So let's say we have dy dx is x plus y. Okay, this is not separable. If this was a product, it would be separable. Here's an initial condition, okay? So I'm going to find the equation of the tangent line. Okay, to, right, dy dx at x equals 1. All right, tangent line to y. Let me erase that. Oops. All right. So the tangent line, you get the slope, right, which is dy dx. I'm doing this at 1, so obviously I'm going to use the 0.13. So I have x plus y, which is 4. So that's my slope. Now, you know the point slope formula. You can write that like this, or you can write it like this. Okay? So I'm going to sub this in. I'll use this version. So I have y equals m times x minus x1 plus y1. All right. So this, now what I'm going to do is I'm going to use, okay, the tangent line. So that's the tangent line to approximate y when x equals 1.1. And the reason you can use the tangent line is because 1.1 is very close to 1, right? It wouldn't make sense if I asked you to use this tangent line to approximate y when x was 5. That would be silly. Okay, so we get y is approximately 4 times 1.1 minus 1 plus 3, which is 3.4. Now, let's say one of the typical questions they love to ask on the AP exam is, does the line over or under approximate the actual value of y? Okay, this is where you look at concavity. Okay, so I get the second derivative with respect to x. I replace dy dx with x plus y. Okay, so the second derivative at 1, 3 is 1 plus 1 plus 3, which is 5. Okay, so that means the curve is concave up. So that means the tangent line, so think about it, if a curve is concave up, right, the tangent line is going to be an under approximation. So since the second derivative is greater than 0, okay, y is concave up, at 1, and therefore the tangent line is an over approximation. All right. Okay, so now let's look at this other method called Euler's method. Okay, this method was actually used in the movie Hidden Figures. Okay, the movie about the NASA women. And you could Google this clip if you're interested in seeing it. Okay, so Euler's method is done more than once so that the curve is closer to the tangent line. All right. And it's an algorithm. It's closer than the tangent line, I mean. Okay, so it's going to be an algorithm, which just means that it's going to be a repetitive method. Okay. So you have dy dx, right, is equal to x plus y, and this was equal to 3. Now, for Euler's method, they're going to have to give you more direction. So we're going to use Euler's method, okay, with a step size, okay, of 0.1. Okay, so this means that delta x is equal to 0.1, okay? To approximate y when x equals 1.2. Okay. So I like to make a little chart. Start with x and y, right? So we started off as 1, 3. Then we have the derivative. So y prime is equal to 4 here. Now to find the new y value, okay, is going to be the old y value plus delta x times dy dx. Okay, so new y is equal to old y plus delta x times dy dx. So my new y, right, would be my old y. Well, my old y was 3 plus my delta x, which is 0.1, times my dy dx. Okay, so this is 3.4. Okay, so that was the tangent approximation that we did in the first problem. Now we know that we have the point 1.1, 3.4. So now we start over. Here y prime is 1.1 plus 3.4, which is 4.5. So my old y is now 3.4 plus delta x times 4.5. So we get 3.85. And that would be your answer because, see, these are the x values are going up by 0.1. It's the y values that are not going up that way. They're going up based upon this formula. So your answer would be 3.85. So when x equals 1.2, y is approximately 3.85. Now you could get a better estimation if you make your delta x even smaller. Okay, I'm going to show you one more problem drawing these little slope triangles. Okay, so again, I have to give you a differential equation, so I'm going to have dy dx equaling y squared times 2x plus 2, and I'll give you the initial condition, okay, that we have 0, -1. All right, so I need to tell you what to do your steps. So we're going to approximate. Okay, f of 1/2 okay, starting at 0 with 2 steps. Okay, so my delta x is going to be my interval 0 to 1/2, right? Divided by 2. So that means each step is going to be 1/4. All right, so first I'm going to do the table and then I'll show you the triangles. So I have x, y. So I start with 0, -1, right? Then dy dx here is going to be y squared times 2 times x plus 2. Okay, so now my new y is going to be my old y, right? So my old y is -1 plus, so I have old plus delta x times dy dx. 1/4 times dy dx. Okay, and then you're going to add that on, right? We're adding this on to the old. So what do we have? We have -1 plus 1/2, which is -1/2. So now we have, remember this is going up by 1/4, so we have 1/4, -1 1/2. Okay, so now we start over. So we have y squared, which would be 1/4 here, times 2 times x, so that would be 1/2 here, plus 2. Okay, so I'm going to make that 5/2 times 1/4. So that's 5/8, right? So now I have my old y plus my delta x times dy dx, which is 5/8. Okay, so doing this math, I get -1/2 plus 5/32, which is -16/32 plus 5/32. So that's -11/32. Okay, so that would be my answer. So at 1/2, my approximation is -11/32. Okay, so what's going on here? If you look at the first triangle, okay, you're starting at 0, -1. Okay, you have your slope, which we found to be 2. Okay, we already know that our delta x is 1/4. So x is moving to the right 1/4, and then y, okay, is moving up 1/2. Okay, so then you get to your next point. So my next point is now 1/4 -1/2. Okay, so now my slope is 5/8. My delta x is still the same. So this was my delta y here, so you don't get mixed up. So my delta x is still 1/4. And then my slope, my delta y, was equal to 5/32. Okay, and so that gave us our final point, which was 1/2 -11/32. Some kids prefer to draw the triangles and do it that way, okay? It's up to you.